last time we recorded question number 51, and that question was a detailed example of the variation of pH at pretty much all the values of base OH minus added for a diacid titration-like curve. And of course, we looked at all these different variations and even at the buffer region. And this was our take-home slide, if you will, or our must-know slide for any type of calculation of pH. Now, the next example, which is actually number 50, which should have come before, is the extrapulation of Ka1 and Ka2 values. So those are not given, but what we are given instead is pHs, and we go backwards. So from the pH, we can calculate and extrapolate the Ka values for a diacid. So with this question, they gave us the moles of a diacid and the concentration of that diacid. We are adding to the diacid some volume Vb of NaOH with a concentration 10 to the minus 1 molar. The first thing is, they said, the first equivalence point is achieved at pH 5.85 after adding a volume Vb, which is actually volume at equivalence, equals 40 mils. So the Vb1 at equivalence is 40 mils. Automatically, of course, the volume at second equivalence, yes, will be 80, and which they didn't really have to tell me that. We could have known that the volume at second equivalence is 80 mils. So that's an extra. They gave you that part, but they didn't have to. The addition of Vb prime of 60 mils led to a pH of 8.08. So what is this Vb prime? Well, if the total, I don't like the fact that they called it Vb prime because we're used to the fact of Vb prime would be what I react extra after the first equivalence. This is the total Vb added is 60. Well, if my volume at equivalence is 40, then my half equivalence is 20. That means 60 mils is the second half equivalence point. Well, then a series of questions was asked. The first one is give me an expression for the reaction and an expression for the pH at equivalence and at half equivalence. Find the Ka1, Ka2 value, and what is the pH at the second equivalence point. Well, answering to the first question, what we need first is the volume of acid that is added. The volume of acid is, we have the concentration, we have the moles. Of course, you all know how to get the volume is going to be number of moles divided by concentration, which is 40 mils. So as well, the equivalence point was 40 mils and the volume of acid was also 40 milliliters. At the first equivalence point, the pH expression is going to be equal to the first half equivalence. The pH is equal to pKa1. You all already know that for all diacids. At the second half equivalence, you also know that the pH is equal to pKa2, which we already have a value because they gave me what is that value at the second half equivalence. Great, so we got that expression. What is at the first equivalence point, I also have an expression for pH. Since at first equivalence point, I have only my species is HA minus, which is amphoteric, and therefore my pH is half, pKa1 plus pKa2. I ask you, please go back to our take-home graph for diacids, and you can easily see these values there. So we were given as well what is the pH that was given at the first equivalence. They told us that the pH at the first equivalence is 11.70. Or we, yeah, they gave us that. Why don't I remember that? Okay. At the second equivalence point, we can have an expression, and we have an expression for it if the concentration is greater than 100 kb, or if the pH is greater than pKa2 plus 1, then we can use pH equals half pKa2 plus half log of the concentration of the dibase, A2 minus. And at the first equivalent, at the initial, we can use that the pH equals half pKa1 minus half log C if the concentration of this acid is greater than 100 Ka and the pH is less than pKa minus 1. Not that if and or, either or, you use either validity. Again, guys, just for us, for diacids or dibases, in those cases, we always only consider them as only monoacids and monobases based on the fact that Ka1 is always greater than 100 Ka2, and if it was a dibase, we'll discuss it in a moment. But this is always the case, by the way, for our first year course. Second year is another story. Okay? Now, at the second half equivalence, if you remember, we were given that pH equals pKa2. So automatically I can get the Ka2 value. That's simply going to be what? 10 to the minus 8.08. So you're done. That's my Ka2 value. Knowing the second half equivalent, that at the equivalence point, we have an expression pKa1 plus pKa2 equals 11.70, then automatically you can get your Ka1 because that's going to be 11.7 minus the 8.08, get the pKa1, and you can get the Ka1. The Ka1 will be 10 to the minus 3.62. Easy peasy, no big deal. Part C, they asked you to get the pH at the second equivalence. Of course, you all know that at the second equivalence of a diacid titration, we have a dibase, only A2 minus. All of the acid got converted to that. And get the concentration of this dibase. Of course, again, we should be aware that this dibase, again, KB1, is only dictated by the first because the KB1 should be greater than 100 KB2. I will add that to my solutions. And let me do that right now. Okay, so always we assume that the A2 minus, that the pH of it is dictated by its first basicity because the KB1 is greater than 100 KB2. Now, of course, I don't really want you to waste any time to check this because, again, for all first year course, this is always going to be the case. Now, calculate the concentration of this dibase now that has been produced, the A2 minus. That's going to be the number of moles of the acid divided by the total volume. Moles of the acid is CAVA because all of the acid got converted to this base, and divided by total volume, which is volume of the acid plus volume of the total base added to get to the second equivalence. So concentration 0.1 of the acid, volume of the acid is 40 mils. And of course now, see, I had to use this number, the volume of the acid, I had to get it. This is volume of the acid 40 mils plus 80 is the total milliliters of volume of the, to get to second equivalence. Now, if they didn't give you this number, you could, you know how to get it because that's just 2 times the volume of the equivalence point. Okay, so get the actual numerical value here. You get a concentration, which is 0.033. Check if that concentration is 100 greater than KB1. Of course, yeah, you have to check, get the KB1, you only have Ka. So what I would do is use this equation directly and check at the end the pH. pH is equal to 7 plus half pKa2 plus, watch out, plus for half log C. Plug it in, you have pKa2, you have the concentration, pH comes out to be 10.43. Now check. Is this pH greater than pKa2 plus 1? Yes, it is. Well, hardly much greater, but it's greater. Therefore, you're allowed to use this equation. Okay. Well, again, don't forget where this equation came from. Go back to the course. See where this equation came from if you have forgotten. Okay. Dibase titration. Okay. And I'm going to go through some detail. This is the opposite of the diacid. Well, you have starting with a high base, and you have two decreases, large decreases in pH value at V equivalences. So at the V equivalence, this is, I have a large decrease in pH, or, you know, quite a sharp one, not very sharp, but sharp enough. And then here I have another sharp decrease in pH, okay? That's at the second equivalence point. So two sharp decreases in pH, but I have actually up to 4 what we call inflection points. Again, the word inflection points means, you know, changing concavity. Here at half pKa, I'm going concave up, and then I start going concave down until I get to my equivalence point. There's kind of like a straight line here, and then concave up again, and then at second equivalence, a second half equivalence, I get a concavity. So there's like this change in inflections, but don't worry about those too much. At V half equivalence, you all know that pH equals a pKa, but which pKa? Yes, pKa2. Why? Because at this point, I start off with a base, A2 minus. As I'm adding acid now to my dibase, because I'm adding acid, this A2 minus is getting converted to HA minus. And at the first equivalence, all of the A2 minus got converted to HA minus. So this is actually a region which is governed by by the HA minus and the A2 minus species, which uses the Henderson-Hasselbalch equation, and which uses the Henderson-Hasselbalch equation between the A2 minus and the HA, and thus you need a pKa2. So that's a little bit different than the diacid because I start with, you know, the A2 minus, and thus I need pKa2 here. Now, we continue to the second half equivalence when the X is 1.5 here. At that point, automatically, you have a pH equals to pKa1. Now, here, what's happening? Now I have my second equation taking place. My HA minus, as I'm adding more acid, where my acid is limiting, is getting converted to H2A, and thus the governing species between in this graph, notice, actually, remove this upper graph altogether. Start from here, go down. This just looks like another weak acid titration. This is a little bit of a, you know, a little bit too sharp of a decrease, but it's fine. Usually, you know, it's not that bad. Anywho, you have the HA minus and H2A species in this whole area, and which is governed by its Henderson-Hasselbalch. And here, when you look at these two species, you need a pKa1. And we're going to go back to a little bit of the pH's. Initial pH, I only have A2 minus in my solution, and that's governed by pH equals 7 plus half pKa2 plus log A2 minus if and only if the concentration of this base is greater than 100 kb, or if my pH is greater than pKa2 plus 1. Now guys, if you notice, we're always repeating the same equations, and guess what? All of these equations, you know, are really at the beginning of the course, either a weak acid or a weak base equations. My HA minus is amphoteric, and you all know that the pH is half pKa2 plus pKa1. That's easy peasy. And At my second equivalence, I only have my H2A species where my pH is likely to be half pKa1 plus minus, now here, this is minus half log C, if and only if my concentration is greater than 100 Ka or my pH is less than pKa 1 minus 1. Again, this is my take-home graph for the Dibase. I will photocopy this or print it out for you guys, and you should really know it. Okay. Remember, for the buffer region, I said that sometimes you could use an easy equation for the diacid. This is the same thing for my buffer region for a dibase. I'm just going to put the equation, and I'm going to tell you to be memorized. Easy to memorize. Between when the x is between 0 and 1, my pH, now again, I have to use pKa2, and this is the log. For the diacid, it was x divided by 1 minus x. For the dibase, you have to flip them, okay? And as well, for the second buffer region, again, just memorize it for those that want speed. Now here in the next equation that we're gonna do, I don't need all of this, of course. You're going to see that I actually don't need many of these pHs, but I thought you have all of them just like the diacid. So number 52. 52 is an example of a dye-based titration. Okay, we titrate 10 milliliters of sodium bicarbonate. Now this is the salt of the diacid carbonate, CO3 2-. We remove the spectator ion sodium. It has the concentration of 0.1 molar, and it's titrated by HCl, which is also of the same concentration, 0.1 molar. Write the hydrolysis reaction and indicate the pKa1, the Ka1, Kb1, and Kb2. Calculate the pH of the dibase alone. And part C, they gave you different X's and they asked you to get the pH. And part D, they gave you different volumes and they ask you to get the pH. So part 1, they want the equation. Okay, so they want the hydrolysis equation, not the titration equation, okay? The hydrolysis equation means in water. I'm hydrolyzing in water. So when I put my base in water, so of course the hydrolysis equation and their corresponding Kb values. So for the CO3 2-, hydrolyzed in water or in water, we get, the water will be my acid, you get hydrogen carbonate minus CO3 minus and OH minus produced, and thus it's a base governed by Kb1 here. Again, products divided by reactants, and the hydrogen carbonate minus, and in another water, because this is actually amphoteric, but in water, it can react as an acid or a base, but here we're acting it as a base. In the form, in its basic form, you will become H2CO3, and again, another OH minus is produced. This reaction is governed by the Kb2, again, products divided by reactants. So that's part A. Part B, they're asking for the initial pH. Well, you have the carbonate, which you should say to yourself, the pH is indicated only by the first basicity since Kb1 is greater than 100 Kb2. Now, do I really have to go and get these calculations? Well, theoretically, yes, you should. Practically, for this course, no. Just assume that Kb1 is greater than Kb2 and move on and say that the concentration, of course, you have the Ka values, you could easily get the Kb values and do the calculation. Let's see. If the concentration is greater than 100 Kb1, well, let's see if it is. I'm going to check it here. I have to get the Kb1 value, which is 14 minus pKb1 is 14 minus pKa2. Watch out, the Kb1 is gotten from the Ka2. So once I have the pKb1, I can check if the concentration is greater than 100 Kb1. And if it is, which it is, use this equation. pH equals 7 plus half pKa2 plus half log C. Why? Again, because this is the equation which governs the pH of a base as long as this condition stands. A substitute pKa2, we have log of the concentration initial for this dibase we have, get the pH. Of course, check it. Is this pH greater than pKa2 plus 1? Yes, it is, and therefore you're fine. Of course, you only need one validity to check. You don't have to do both of them. Titration of 10 milliliters of the carbonate with HCl. So when they did this titration, we can find the volume at equivalence or at first equivalence. So concentration of the acid times volume of the acid equals concentration of the base times volume of the base equals the concentration of the acid added times volume of that acid at equivalence, because the moles of acid equals moles of base only at equivalence points. Get the volume at equivalence, and you get that volume at equivalence is equal to 10 mils. So great, the volume of the acid is 10 mils, and the volume, the volume of the base is 10 mils, and the acid at equivalence is also 10 milliliters. So the calculations become easier when it's like that. Get the pH when X equals 1.2. Okay, when X equals 1.2. I'm going to do it the long way, then the short way, okay? At first equivalence, we have 10 milliliters of the A2 minus, 10 milliliters of the acid will react with the A2 minus, and we're going to have 2 milliliters left over to react with the A2 minus. Now, where did we get this? We converted the X, the 1.2, we saw how much volume of acid was added whenever we have that X value. So if X equals V acid divided by V acid at equivalence, we have the V acid at equivalence, find the volume total of acid added. So that really, they could have asked you the question in terms of that I added 12 milliliters of acid, what happens? Well, you know that 10 milliliters is going to react with the A minus, and that will, remove all of my first acidity. And that whatever is left over will react with my base. Or remember, 12 minus V at equivalence, you're left with 2. So 2 is going to react in the second equation, which is hydrogen carbonate plus the added acid H3O plus becoming H2 carbonate. So here, you only have 2 milliliters reacting. Now, if you were to put here 12 mils for the acid, you will see that this acid will be in excess, and the excess amount reacts with the hydrogen carbonate minus as a base. So, it depends on how you do it. You could have put 12 here, you would have had remaining acid, and that remaining comes out to this side. pH is, what are you left with here? Of course, you have left with the acid and its conjugate. And of course, this is after the first equivalence. This is a value. We're using Henderson. And if you look at these two couples, of course, the pKa, which pKa, pKa1, because these couple are governed by the Ka. Substitute in, we have the base and we have the conjugate acid, 0.8 and 0.2. All right, you get a pH of 6.9. Now notice all of this look at what I would have done if I was, in a class. I would simply had memorized that if I'm in a region of the second, after the second equivalence, after my first equivalence, that means that my pH is governed by this buffer region where my X is between 1 and 2. And if my X is between 1 and 2, and I have memorized this equation very well, look at this. 2 minus X, what's the X value? It's right there, 1.2. 2 minus 1.2 is 0.8. 1.2 minus 1 is 0.2. Wow, I have this already. So guess what? Using this equation really, really helps out. Okay, then you don't have to do this full chart or even thinking of calculating how much volume. Okay, it helps out. Okay, when my X is 2, that's my second equivalence, okay? And we can go ahead and find the volume VA added at that point, which is 20 milliliters of the added acid. I've known because if the equivalence point is 10, the second equivalence is obviously 20 mils. But you can use your X value to get that. Second equivalence is my H2 carbonate, the diacid. And of course, that's the pH of it is going to be governed only by the first acidity, as long as the Ka1 is greater than 100 Ka2, which is again always the case of our first year course. You can go ahead and check indeed if Ka1 is greater than 100 Ka2 if you really wanted to. I wouldn't. Okay, because it's never, again, it's never in this course. H2CO3, the concentration of this diacid is going to be CbVb, because all of the base got converted to this acid, divided by the total volume of the base and the acid added, HCl added, which is that second equivalence, which is again 20 mils. The V of the base was 10 mils, concentration of the base was 0.1. Do the calculation. Again, you always get this comes out to be 0.00333 again. If that concentration is greater than 100 kb, sorry, not ppb, it is, we use pH equals half pKa1 minus half log C. But guys, if it isn't, what do I use? If it isn't, what do I use? Yes, the quadratic equation from the Ka1 expression, which should be X squared divided by C0 minus X, solve for X, and since it's an acid, the X is H3O plus. Okay. Now we just substitute pKa and the concentration which we just found, and you get the pH. And if that, check it, if that pH must be less than pKa minus 1, and indeed it's much less than that, and therefore you're all happy and you are done. Now part D, they're giving you now the volumes, okay, and they gave me the volume. Or I can get my X as well. From the volume, I can always get the X. The X is this volume divided by V equivalence, so this is 0.6. What am I going to do? Well, I'm going to say this is before equivalence because my X is 0 and 1, or my V acid added is before the equivalence point, before 10 mils. I would have memorized this equation, pH equals pKa2 plus log of 1 minus X divided by X. Don't forget these. The ratio should be done before the log value for your calculation. And then you are done. Well, let's check it in the fast way first. So let's see. If my X is 0.6, then my log value here will be 1 minus 0.6, which is 0.4, and my X is 0.6. Do the calculation, and you see that the pH will be the same as if I do this whole chart thing. Well, let's do it with the chart. Okay, so before equivalence, I have this equation as my governing equation. Carbonate plus H3O plus becomes hydrogen carbonate plus water. Carbonate, my CbVb and CbV. The number of moles of acid added or HCl added will be 0.1 times the volume, again in milliliters, so these are millimoles. Okay, so this is the limiting amount, so that's going to tend to 0. Again, epsilon, you want to call it, that's fine too. This is going to be 1 minus 0.6, the limiting reagent, which is going to be left over 0.4. The hydrogen carbonate is 0.6. So you're left with a base and its conjugate, which is, you use Henderson. Which Ka value do you put here? Look at the two species. Yes, these two species require pKa2. Substitute, and voila. The same exact pH and the same actually exact concentrations here as if what we did with the X equation. At equivalence, at the first equivalence, when my volume is 10 mils, of course, all you have left is hydrogen carbonate, HCO3, which is an amphoteric material, and then the pH equals half pKa1 plus pKa2, and then your pH is 8.3. All right.